Assalamualaikum everyone. Welcome back to the CFD learning series. In the previous video, we developed and solved the CFD case in ANSYS Flink, and we completed the main step of the solution. Although we have imported a geometry preparation and mashing, it was already be done of that case. Okay, so in the previous video, we just learned how to set up the boundary condition, solution method, and how to run the simulation. In this video, we will utilize the same solve case of the CFD, okay, and the real engineering understanding come from the post-processing, where we analyze the result and convert the numerical data into the meaningful conclusion. So, in this video, we will discuss how to perform post-processing of the solve Flynn case, okay, uh, we will learn how to visualize the flow behavior using contour, velocity vectors, streamlines, pressure distribution, temperature distribution, and other important results which we can develop or plot depending on the case requirement. So we will also discuss how to interpret these results from an engineering point of view, because in CFD just obtaining colorful images is not enough at all. Now we must understand what these results are telling us about the system performance, flow pattern, pressure drop, again very important variable, circulation zone, high velocity region, and possible design improvement. So by the end of this video, you will be able to open a solved plain case, extract important result, prepare professional plots, and explain your CFD findings clearly in the report, or you can present it whatever the result you have developed in your case. So let's start with the post-processing of our plain simulation and see how we can convert the result into useful engineering knowledge. So from this window, you can see I have already opened our case, and it was previously being simulated uh, with uh, with the residual trend. These are the residual trend which I had explained in the previous class, in the previous video, in fact. And our solution converged on 129 iteration, and we have get the important results. So now we will move forward and will develop more results. So first of all, we will solve the case, like we will go to the reports, and then we select the flexes and select the setup, mass flow rate of in out, flow in, flow into, and outflow. Okay, and we want to calculate it, so then this is the net result uh, of uh, the work. And the next is to develop the graphical contour. So first of all, we will go to the graphics, and there we will select the contour. Okay, and with that we will select the setup here with filled, and obviously we are, in our case, we are interested to investigate the temperature, so I will select the temperature here, and then we have a minimum and maximum option. Just leave it. With that, we are supposed to select the pipes, so pipe 1 and pipe 2. I'm selecting both of them, and then we just have to press the display button. Now you can clearly see the temperature contour is available and on our screen, and representing different uh, values of the temperature. Okay, and the next is, okay, if we are interested to develop the contour for uh, turbulence behavior of the flow, so for that we will select here as turbulence, and you can see here is the option available for the turbulence. And now vol y plus is again a very important uh, uh, variable that reflect out that how the calculation is being accurate, or we can assess our system. So I'm not gonna explain y plus right now, but uh, I will make a separate video for it. Okay, so but we can display that result here, and on the basis of that we comes to know that the maximum value of the y plus is moving around 1.17 into 10 raised to power 1 positive 1. So that means it is around 11.8 something, which is also coming in this uh, tabs option with the minimum value of the 0 with the maximum value of 11.668. So now these are the results which so far we have developed in Flink. Now we now I will save my this complete work. Okay, and for that I have to go to the file and write and click the case and data options. Okay, here available. So it will ask me where to save it. So I'm gonna overwrite it. Okay, because it's already saved, and you can see here in the console it is now notifying that writing the and everything is done. So that reflecting that our case is successfully and its data even successfully saved in a particular file, um, whose location is also coming in this line. Okay, so now we will go to our CFD post processing, and we will turn it on. So here now again we have to import all the file. So for that we will go again to the file, and we need to load the results, and that file is right now on CFD Laxer number 1. Okay, we need to select the data file. Okay, and we need to open it. So say this. Okay, and now the geometry is successfully loaded, and although we cannot see anything because all these things are unchecked, like inflow 1, inflow 2, outflow pipe 1 and pipe 2. So one by one, if when you begin to check it, it's begin to appear in this window. Now we are supposed to develop it is contained now right now it's constant color. So if we need to if we want to modify or develop a better result for our case, so we will press the right click, we will select the edit option, and then these options will be further appear in front of us in the bottom details. Okay, so here you can select variable. Okay, and on which variable based. Well, we know that our pressure is throughout constant, and we define our operating condition as 101.325 bar. So pressure is not a changing variable. Our system is majorly depends on the temperature, and its behavior is changed from both of the inlet pipes, and obviously then both fluid will mix it up, and at the end of downstream we have a very different temperature than what we are receiving from the inlet of both. So similarly we will select the temperature option and the range as global. Okay, you can use as a user defined as well, but yeah, software will develop its own uh, results. Okay, now we have applied it, so only pipe 1 pipe 2 result is displayed here, and we know that we define the temperature of the fluid in pipe 2 as 400 degrees centigrade, which is available here. majority of the color of the fluid appearing in this portion is with the red. So we need to define pipe 1 as well in a very similar way by pressing the right click and then edit, go selecting the edit option, and on the same way we will select the variable here, and obviously the important variable is the temperature, and we will remain, everything will remain same, and we just need to press the apply button to get these results. Okay, in the same way you are supposed to press inflow 1, and you are supposed to edit it, variable, temperature, and apply. Now you can see here this is representing properly, although this color is still not what it should be. In the same way, we don't have a good representation of the color in the downstream too. Okay, so in the same way we will press the inflow 2, we will press the edit button, and we will select the variable, temperature, and apply. Now you can see this is completely appearing and reflecting the temperature which is available in this color gradient. And the remaining thing is the outflow. Okay, and the outflow temperature uh, is again need to be added, and it remains constant. We need to select it as a variable with temperature, and we need to press the apply button, and you can now see the results are deviating what it was present in way before than that. Okay, so it's the first way through which you can develop the temperature contours. Now if we want to further modify or develop different types of the results, so we want to check out only the result along an axis in a 2D format, so we will go to the location, and from there we will select a plane. Okay, and let's say the plane is XY, or sorry, it should be XZ, because we want to see the 2D result of this geometry, so it should be XZ. Okay, and press OK, and then we need to further define it like the geometry um, as all domain. So here we will just select the ZX. Okay, and then we need to go to the color option, and in color we need to select the variable again, and now we are interested to develop the velocity distribution or behavior on the very same way, and just remaining thing is just to press the button apply here. So for that we just need to uncheck it all, and we can clearly see now the XY plane is checked, and we can easily see the 2D data from here. Even if I want to move the y-axis value, it will apparently provide me the detail of the values, like here in the beginning we have select y is equals to 0, or if we want to go on the maximum y value, so you can clearly see that value is appearing here. And in a similar way, if uh, I want to check the y value at some minimum level, so it ultimately move or shift towards the other portion of uh, your pipe. Okay, and apparently it's providing you the result of, you know, um, most of the layers, all the layers velocity values are near to the zero. and we can clearly see that they are comprises of the blue to light blue color gradients. Okay, so similarly, if actually this is the very high diameter and the upper diameter of the pipeline is lower than uh, the what we have for pipe uh, 1. Okay, so that's why it's not representing any color or profile or gradient representing the streamline velocity here in the upper region. But let's suppose we just reduce the margin, so you can clearly see the boundary layer of the upper pipe is now capped. We can capture it as well. So obviously we will every time we'll see at the middle part, and we will apply it, so you can clearly see the middle geometry of our contour of our geometry. And in the same way you can develop here, this is the velocity results, here you can develop the temperature result as well. Okay, in a very same way. And apparently if you are interested to um, determine like the results like pressure, so this is you're representing the pressure behavior, but the range is not very much high or low, almost near to upper region. Its value is moving near to the upper region. And if you want to rectify the density, so this is the way the density of the fluid, as it's heavily depending on the temperature. So its trend is quite similar to what we are receiving for the temperature. Okay, because we utilize the ideal gas equation, and throughout our system is the pressure does not changing so drastically, so it's providing you this very same trend as what we are receiving for the temperature. Okay, so numerous variables are available, and you can alter them, and you can rectify their values accordingly. But let's suppose if we are interested to uh, get a streamline result, so this is the streamline option, this is your particle track. Okay, if you are interested to rectify the particle track, you can utilize this option. Right now we are selecting the stream line result, and let's say it is stream 1. Okay, and so here all domain, and then we will select now we will select the option um, y exact, and the direction should be forward and backward. Okay, and let's say we are selecting 40 points across the geometry, and just apply it. So you can see here it's representing the streamlines, and obviously why it is representing like this, because we have not unchecked our exact planes. So once we unchecked it, so it's only representing the streamlines results. Okay, then on the same way, if we are interested to determine the vectors, okay, at any position of your, like if we are interested to rectify the velocity vectors direction at any portion of the pipeline, so we can rectify it, okay, with this option. So we have to select OK, and then uh, the two axes which are important in the vector formation are y and z. Okay, because across the diameter, this is across the diameter, the velocity vector's direction will be more important, so which is belongs to the plane xz. So here ultimately we have to select the location as plane, uh, YZ. We need to add this location. Okay, plane, and then we have should have YZ plane first, and in YZ plane, this should be YZ plane, and we need to apply it, and we need to uncheck it. Sorry, YZ plane. Okay, and YZ plane is now added. Now we will move towards the vector. Okay, and vector 1 is defined, and in which we need to define the location in the same way. YZ axis is selected. um, we need to There are so many options available for this. Okay, this will represent the sample, so the sample should be uh, face center, and then in reduction, the reduction factor is remains same, and then which the which variable we are interested. So obviously there are other options as well, like water shear or velocity in the fifth frame. So we are selecting only the velocity, and in the same way the color should be plot, and symbol should be arrow 3D, and it should be the size should be 1.5, so we can clearly see it. Okay, and now apply it. Now we can see its position, value, and its interface. But let's suppose it is right now at its position can also be changed. Okay, so right now it's representing the inlet position velocity vectors. Okay, so you can see here these are with the vector formation, and we can clearly see the arrowhead and the tail of the tail of the arrow. Okay, but let's suppose we are interested in let me show you the complete geometry. Like, it is right now the inlet portion of pipe 1, and we are interested in rectifying the velocity vector at this joining part. Okay, so for that we will have to modify the our uh, YZ axis. Okay, we will go for their with added position, and right now we can clearly see all the results we're receiving with z is x is equals to 0. uh, Let me just uncheck it. So it is where when x is equals to 0. So I just need to go in such a way that the x should be at the middle portion. So let's say it's might be representing here. Okay, but we are supposed to go a bit before than that. Okay, so we just move backward, and now we can see the velocity vectors at this position, and clearly understand that whether there is a band vectors are also available with certain angles. Okay, furthermore, if uh, let's suppose we are in our streamline result, let me just uncheck this vector. Okay, and we again move towards our streamline results, and I am interested in rectifying the particle movement of along this passage. So with the option available here with the name animation. You can click it, and here you will select the stream one and play the video. So it will represent the actual uh, velocity or position and the path line of the particle, how they are moving. Okay, so in that way you can also assess, like at the beginning of our the series I had told you, in food engineering it's very important that we provide heat treatment or pressure treatment with a particular span of the time, and we need to make sure that every layer possess that duration of the temperature for a particular time, and that time should not be very longer as well, because ultimately if we over treat our food product or over process our food product, that ultimately denatured the nutritious content of the food. So again, these type of results will help us in understanding uh, the actual how each layer hold up, or how much times it will stay in your geometry or in your process. Furthermore, you can slow, or if you want to study the relative motion of each layer, so you can slow it down, and similarly you can speed it up as well. So this is a very fast result. So it's depend upon your process, like if your process is very slow, so you can speed it up, and if your process is very fast, so you can slow it down in order to investigate the relative velocities of each portion of the section. So that's it. I hope you understand a lot of variety of the result development with the help of uh, post CFD processing technique. And apart from that, there are more options also available that you can develop the correlations, the modeling as well. But right now we are at the stage of a very beginning portion of our course, so I believe that it's enough to understand for right now, and then we will touch some of the very important variables like y plus, and obviously the criteria through which we select the turbulent models or models available in this software, okay, as per this the process. Okay, so that's all for today. Thank you very much. I hope you enjoy the video.